Hello everyone, my name is Yezhou Wang. I'm from Shanghai Jiao University. It's my great honor to present our work in NSDI, which is a new method to improve acoustic sensing and communication using metasurface. Nowadays, acoustic sensing and communication are becoming really pervasive and popular, and there are a lot of related applications. For example, acoustic sensing has been used for human-computer interaction interfaces, and for healthcare, there are fault detection for the elderly and body function test applications. Acoustic sensing is also used in VR and AR area and drone platform. However, there are two major challenges for acoustic-based applications. First, the signal attenuates by square of distance in free space, which makes the SNR decay rapidly. Second, considering a real-world scenario, the reflection from objects in the environment causes multipass problem. The presence of multipass introduces merge peaks, which will increase the sensing error. Conventionally, there are two ways to solve the challenges. The first solution is using algorithms at the receiver side. Currently, many algorithms can be used to improve SNR, such as filtering, beamforming, deep learning, etc. However, as seen in camera bound, the improvement of SNR using algorithms is limited. Another solution is using ultrasonic phased array to beamform the outgoing wave acoustic signal into desired directions to increase the signal strength. However, it is bulky, expensive, and power-hungry, which makes it hard to popularize. So, can we come up with a more effective way to solve the major challenge? We found that passive acoustic metasurface can be used to enhance the transmission channel. To understand acoustic metasurface, the best way is to understand its internal structure. Here we give an example of a typical metasurface which consists of 16 by 16 cells. Inside each unit cell, we can use parallel steps to change the propagation path of acoustic signals. After the incident wave passes through a unit cell, the phase delay is introduced. The different path lengths will introduce different phase delay at the output, making each unit cell behave like a mini speaker. By carefully arranging the unit cells, the metasurface can interact with sound differently. For example, if there is a single speaker, we analyze two of the different sound passes, the blue one and the green one. The blue and the green incident wave have different phases when it reaches the metasurface. We can introduce different phase delay using different cells for the blue one and the green one. By doing this, we can make two outgoing waves have the same phase delay. In another word, metasurface gathers the sound power in blue area into red area, making sound propagate farther. There are several advantages of using metasurface instead of ultrasonic phased array. Firstly, since metasurfaces are typically 3D printed, they are considerably more cost-effective compared to phased array. For instance, the most affordable DIY phased array costs around $200. Secondly, metasurface requires no power supply. Since metasurface do not require power supply wires, metasurface is allowed to be manufactured in a very compact form. And metasurface can offer significant power gain. However, there are still some limitations when using metasurface, because passive metasurface only have fixed beam direction. Let's consider a real-world scenario using metasurface to improve SNR. If we use metasurface to improve SNR performance, Because the metasurfaces have fixed beam direction, we cannot get adaptive steering with a typical passive metasurface. But in sensing and communication scenarios, the target is not stationary. It requires the beams to focus on different directions. So how to get adaptive steering for sensing and communication? Our solution is to combine a small speaker array and a passive metasurface. The intuition is that the small phased array is used to provide control capability. The metasurface is used to focus the outgoing beam. The combined configuration can achieve dynamic beam steering and high SNR. There are three key components to realize our proposed model. The first component is designing an optimal metasurface which is capable of handling steered beams in a wide angle, not only considering the fixed direction as the traditional passive metasurface do. The second and the third components are designing the codebook and the geometry of our speaker array with the presence of metasurface, because the impact of metasurface should be jointly considered. To optimize the previous three components, we need to first model the propagation of sound in air. In our model, we divided the sound passes through the metasurface into four parts. The first part is the sound played by each speaker. We use W to denote the outgoing speaker signal from speaker array. The second part is the propagation of sound from speaker array to metasurface. We use H to denote the channels between the speaker and the metasurface. Each signal at the metasurface side is a product of channel matrix H and the speaker signal W. The third part is the impact of metasurface. As we mentioned before, metasurface brings different phase shift at different cells, with G to denote this part of impaction. In the first part, we model the beam pattern of outgoing wave. We use KD to denote the steering vector corresponding to direction D. By multiplying the steering vector KD and the metasurface outgoing signal, we can get the final signal beam pattern RD given steering direction. We can calculate the result of all steering direction by changing the code word W and calculate the signal strength at all directions using steering vector K. The sound power P is the square of received signal amplitude R. After we calculated the received signal power of all directions, we can have a matrix of power P. Each line of the matrix represents the beam pattern of one steering angle. The next step is to derive optimization objective from P. The optimization function we use consists of three parts. The first part is to maximize the signal strength along each of the desired angles. It is a diagonal of the received signal power matrix. The second term is the variance of power of each direction. This part is used to avoid some dead zones for certain directions and produce a wide steering angle. The third term is the sum of non-diagonal peaks. It is used to minimize the power side lobes and correct directivity. Putting these three terms together, we get the final optimization model. And we perform joint optimization to get the final speak codebook W, optimal metasurface theta, and speak geometry X. Here in my hand is the final optimized acoustic metasurface. As you can see, it consists of 16 by 16 grid of cells, and the design of this metasurface is resulted from the optimization of the shown loss function. Next, we show our experiment setup. Our experiment platform consists of three parts. the speaker part, metasurface part, and the microphone part. We use Bela platform for signal synchronization. Some separated amplifiers are used to power the speakers. Here is the real function part of our system. It only consists of a small phased array and a passive metasurface, which is much smaller comparing to the bulky phased array system. We first evaluated the SNR performance of our system. We use normalized amplitude to represent the signal strength at the receiver side. This figure shows the power gain at different steering angles. As we can see in the figure, the single speaker is omnidirectional, but the power is low in all directions. When metasurface is added, the amplitude has a significant improve at the beam direction. However, only use a passive metasurface is not able to provide steering ability. The amplitude drops fast when the azimuth angle increases. The phased array solution also performs well on all directions. However, the improvement provided by phased array is limited when the size of phased array is small. The right line is our solution, combining the phased array with metasurface. The signal strength has significantly improved comparing to the scheme using single speaker or a small phased array, and our scheme achieves a wide steering angle. Comparing to the scheme that uses only phased array, our scheme is comparable to 70 speakers in terms of power gain. To illustrate why our scheme has such a great SNR gain, we show the beam pattern of our scheme and phased array. As we can see in the figures, a small phased array is only able to focus beam in azimuth direction, but adding a metasurface provides the ability to focus beam in both azimuth and elevation direction. Beam width is important in multipass problem. We further compared our scheme and phased array system in beam width. The result shows that our scheme is comparable to 9x16 phased array in terms of beam width. The next part we show our scheme's performance in sensing. In distance estimation, our scheme increases sensing range to 2.2 to 2.6 times, compared to phased array scheme at various steering angle. In area estimation, our scheme increases sensing range to 1.9 to 2.5 times, compared to phased array scheme. The next part we show our scheme's performance in communication. The following figures illustrate the communication bit error rate performance of each scheme. Our system demonstrates a wide steering range and significantly improves the communication range, as shown in the figures. To evaluate communication performance, we calculated the frame error rate. Our scheme has increased the sensing range to 2.4 times as compared to the phased array scheme at various steering angle. In conclusion, in our paper, we develop a novel acoustic system that uses acoustic metasurface and phased array and achieves the power gain comparable to a large phased array at low cost. Our model jointly optimizes acoustic metasurface and phased array configuration. The increasement in SNR can be translated into high accuracy in distance and AOA estimation in acoustic sensing, and a large communication range in acoustic communication. We build a practical system and use extensive experiments to show the improvements brought by the system. This concludes my talk. Thank you for listening, and I'm happy to take any questions.